Hello everyone, my name is Mesomachi. I'm an instructor at Special Maths Academy. So in a bid to help students that have qualified for the third round prepare, we'll be creating solution videos for last year's third round. Don't forget to like, share, comment, subscribe, and share with your friends who will be preparing for the third round, the Mathematics Olympiad. Enjoy the video. Good day everyone, and welcome to another problem solving session with Special Maths Academy. Today we'll be looking at the last year's third round of the Nigerian Mathematics Olympiad. So you can see the question here, let P and Q equals to P plus 2. So that implies that Q is the bigger prime here, between primes, okay? So consider the Diophantine equation. So we have n factorial plus pq squared equals to mp all squared, and m and n are greater than or equals to 1. So if m is equal to p, find the value of p and ii. How many solution quadruple pqmn does the Diophantine equation have? Now, looking at the I and ii, it's obvious that if we solve ii, we have I, because ii is asking for all possible solutions. Okay, so yeah, the mean there, primes are everywhere, prime numbers everywhere. Okay, so I'll just remove the mean and then we begin. Okay. Okay. So I'll be writing down some important milestones. So milestones. Okay. So A, from P and Q being twin primes and Q equals to P plus 2, it implies that so Q equals to P plus 2, both primes. Implies that P is not equal to 2. Because if P were to be equal to 2, then Q will be even. Q will be 4, and 4 is not a prime. Okay? So now, B. Yeah, obviously P is less than Q. So we have to observe that P is less than Q. And then C. So let's look at n factorial. Let's look at this Diophantine equation modulo P. So if you take mod P of both sides, what do you have? You have n factorial plus pq squared congruent to mp all squared mod P. So we have n plus 0 because we have pq squared. It's congruent to 0 mod P. So this implies that P divides n factorial. Okay? So it implies that as you're listing the numbers from, because you have that n factorial is, you're just listing the numbers from 1 to up to n. So as you're listing the numbers from 1 to n, it means you must encounter P. Because P is prime, there's no other number that will divide P apart from P or 1. Okay, so for P to divide n factorial, it means that P must be somewhere here. So P somewhere. So what does that imply? It means that P can be at most n or less. Because I mean, if n were equal to P, we'll have P factorial, and then the last term here will be P. So, but if n is, less than P, so if n is, let me say, equal to P minus 1, so P minus 1 factorial, we can't find P anywhere. So it means n must be greater than or equals to p. Okay, so I'll just erase this. So this implies that n is greater than or equals to p. Okay. So n greater than or equals to p. Now let's take modulo p squared. Okay. So modulo p squared, we have that n factorial plus pq squared must be congruent to 0 modulo p squared. Okay, so we see that using modulo p squared, just directly like this, doesn't really help us so much because we can't really conclude anything from here. We can't really conclude much from here, or else there's something that you can see that I can't see. So let's go back to the Diophantine equation and try and factorize it and see what we can get. Okay. So now this Diophantine equation, n factorial plus pq squared equals to np all squared. We can isolate the n factorial and see if we can factorize what we have on the right hand side. So m squared p squared, I'll just open the bracket immediately, minus pq all squared, and minus pq squared rather. Okay. So what does this give us? This gives us that n factorial is equal to p into pm squared minus q squared. Okay. So now, for p squared to divide this, so suppose p squared divides p into pm squared minus q squared. Okay, what does this give us? This gives us that, because you can cancel out the p from both sides. Okay, so that's simply saying that suppose p into pm squared minus q squared all over p squared is a member of integers. So it implies that we can cancel out p. Okay. It implies that pm squared minus q squared all over p is a member of integers. Okay. So this implies that p must divide pm squared minus q squared. Okay. Now we know that p divides pm squared. P divides pm squared. So it implies that p must divide the difference. So pm squared minus q squared, which is equal to what? Q squared. So we have that p must divide q squared. But since these are both primes, we get a contradiction. So it means our assumption from the beginning was wrong. So this is same thing as this is equal to n factorial. So it implies that p squared does not divide n factorial. What does this mean? It means that when we're listing the product of n factorial, we can only have at most one multiple of p here. Because if we have two multiples of p, then p squared will obviously divide it. So only one multiple of p. Somewhere. Only one multiple of p. Let me write this my p. Well. Okay. So it means 2p. 2p is not here. 2p cannot find himself there. So it means that 2p is greater than n. Okay. So take note of this, very important. Let me try this well. 2p greater than n. So take note of this, very, very important. Okay, so I'll just erase this and then we go to the next fact that we need to prove. Okay. So fact D. We want to show that Q does not divide M. So we just assume. So suppose Q divides M. What does that imply? That implies that Q divides, so let's just put it this way. Okay, so we have n factorial is equal to pq squared, rather mp all squared minus pq squared. Okay, so if q divides this, obviously q divides. So if q divides m, what does that imply? How to imply that q squared divides m squared. Okay, and this implies that q squared divides mp all squared, and now q squared divides pq squared, because pq squared is obviously a multiple of q squared. So what does this imply? This implies that q squared divides the difference. So let me just write this: mp squared minus pq squared, which is equal to n factorial. So as before, what we've been analyzing since, so this implies that q squared divides n factorial, so which implies that n is bigger than or equal to 2q. Okay, but 2q is bigger than 2p. So this is a contradiction from fact C, that 2p is bigger than, as 2p is bigger than n, which is bigger than p. Okay, so basically what we're getting here is, if we complete this, we have that n is greater than or equal to 2q greater than 2p, which is bigger than n, which is bigger than or equals to p. So we get that n is bigger than n, which is a contradiction. Okay, so what does this imply? It implies that our assumption was wrong. Okay, so q does not divide m. Okay, so just erase this quickly. Okay, so now I want to see how big is n in terms of q. So suppose n is bigger than or equal to q. Alright, or we can, if you prefer working, so suppose q is less than or equal to n, which is the same thing. So it means when you're counting numbers from 1 to n. So suppose you count q first. Okay, so what does that imply? It implies that q will divide n factorial. Okay, and what is n factorial? So n factorial is equals to np squared minus pq squared. So it implies that q divides np squared minus pq squared. Okay, so now it means q divides m. squared. So since Q and P Q and P are prime, so it means Q does not divide P. So what does this imply? So it implies that Q divides M squared. And since if a prime divides a perfect square, the prime divides the square root. So it implies that Q divides M, which is a contradiction from fact D. Okay, so it implies that what we assumed was wrong. So it means that fact E or milestone E, Q is bigger than N. Okay, so what does this imply? We already know that N is bigger than or equals to P, so it means that Q, which is P plus 2, so P plus 2 is bigger than N, which is bigger than or equals to P. Okay. So what does this imply? It means that we'll consider some cases. So now we've broken down our work into some cases. If N is in between P, that is, if N can, it means N can take the values P and P plus 1 only. Okay. So if N, so okay, let me just put it. So it means, so E implies that N is a member of the set P and P plus 1. Okay. So if N is equal to P plus 1, so this is same thing as Q minus 1. Okay. What does that imply? We have that Q minus 1 factorial is equal to, so this is just equal, I'll just factorize this. This is the same thing as P into PM squared minus Q squared. So Q minus 1 factorial, this is the same thing as P into PM squared minus Q squared. So we can take mod Q, so modulus Q. And why are we taking modulus Q? Because we know that any prime, so if P is a prime, by Wilson's theorem, P minus 1 factorial is congruent to minus 1 mod P, if and only if P is a prime. So okay, so taking modulus Q, so this is Wilson's theorem. So taking modulo Q on both sides, so it means that minus 1 is congruent to P into Pn squared minus Q squared mod Q. So this Q squared can disappear here, so we have minus 1 is congruent to P squared M squared. Okay. Now we know that P is equal to Q minus 2. So we have minus 1 is congruent to Q minus 2 squared M squared. Okay. So we can quickly get that minus 1 is congruent to 4M squared mod Q. Okay, so we have that (2m) all squared is congruent to minus 1 mod Q. So let me just So we have 2m squared congruent to minus 1 mod q. So let's erase this. So what does that imply? It's well known that if a perfect square so it's well known that if so now a well-known term, if we have x squared congruent to minus 1 mod p, so x is an integer and p is prime. It is well known that x squared, it's well known that p rather is congruent to 1 mod 4. Okay. So now, what does that imply? This implies that Q is congruent to 1 mod 4. So Q is congruent to 1 mod 4. So we can replace Q with P plus 2. So how that P plus 2 is congruent to 1 mod 4. And so we have that P is congruent to negative 1 mod 4. So I have P is congruent to 3 mod 4. Okay. So now what does that imply? This implies that n factorial, you can take mod 4 of this. So you have that n factorial. So I'll show you this. N factorial, which is congruent to p into pm squared minus q squared. So we're taking mod 4. So p is congruent to 3. We have 3. Okay. M squared is congruent to 1 or 0. Mod 4. So first of all, let's see why m squared should be congruent to 1 mod 4. M squared should be congruent to 1 mod 4 because you see that m has to be odd. Okay, so how can we see that m has to be odd? So we're giving that none of the primes is 2. So it means if we take mod 2 of both sides, n factorial, which is already bigger than a prime, so it means n factorial should be even. So n factorial is greater than or equals to p, which is bigger than 2. So n factorial should be even. So if you take mod 2 of both sides, we have that this is going to be 0 is congruent to. So since p is congruent to 1 mod 2 because p is odd, so it's going to be m squared. So I want to see what m squared is congruent to. Minus p and q are congruent to 1 mod 2. So this is 1 mod 2. So it means that m squared is odd and hence m is odd. So it means that all perfect squares, all odd perfect squares are congruent to 1 mod 4. So that's why I just immediately put 1 for m squared. Okay. So it's easy to see that this n factorial is going to be congruent to this mod 4. And so we have that n factorial is congruent to, so we'll just simplify this. This is going to be 3 into 3 minus 1. So that is going to be 3 times 2, which is 6. So n factorial is congruent to 6. 6 mod 4. Okay. So this implies that n, since n factorial is not congruent to 0 mod 4, it implies that n is less than 4. Okay. So it implies that n is either equal to, so since p is greater than 2, so I'll also put since p is not equal to 2, this implies that p is greater than 2. So it means this is greater than 2. So it implies that n is equal to 3. Okay. So if n is equal to 3, we have that, so I'll just quickly get it. Remember what we assumed, we said if n is equal to p plus 1. So how that, and it means that p is going to be equal to n minus 1, that is 3 minus 1, 2, and q is going to be equal to 4. These two are not primes, so it means that n is not equal to p minus 1. So it means our milestone f is that n is equal to p. Okay? So I'll just erase this quickly. So I'll also put on our facts here. So before this, I'll put on our facts for f. I'll put that m is odd. Call that m is odd. So you can also take mode 2 on both sides. So m is congruent to 1 mode 2. M is odd. And then our fact G is going to be that P, n is rather equal to P. Okay. So we have n is equal to p. What does this imply? This implies that p factorial, so we'll just replace quickly with p factorial. So p factorial is equal to p into pm squared minus q squared. So we can divide both sides by p, and we get p minus 1. So once you have a prime factorial, you want to get that prime minus 1 factorial because you can quickly apply Wilson's theorem. So equal to pm squared minus q squared. Okay, so now I can take modulus p of both sides. I have what? Minus 1 congruent to, this is going to be 0. So congruent to minus q squared mod p. Okay, so I have q squared is congruent to 1 mod p. Okay, so what does this imply? We can replace q with p plus 2. So this is p plus 2 all squared congruent to, this is going to be congruent to 4, because we can quickly put p equals 0. It's congruent to 1 mod p. So what does this imply? We have that 3. So our 3 is going to be congruent to 0 mod p. So I have p divides 3, and p is prime, so p is not equal to 1. This implies that p is equal to 3. Okay, and if p is equal to 3, this implies that q is equal to 5. So now we just solve for m. So we have 3 factorial, which is going to be 6, is going to be equal to 3 into 3m squared minus 25. And so what do we have? We have, so I'll just erase this. So now we just have a simple equation to solve. So I have 6 is equal to 9m squared minus 75. Okay. And so we have 75 plus 6, so this is going to be, alright, we can divide through by 3. So we have dividing through by 3. So we have 2 is equals to 3m squared minus 25. Okay, so that's just an easier way to go about it. 2 is equal to 3m squared minus 25. So we have that 25 plus 2, that's 27, is equals to 3m squared. Okay, and so we have that 9 is equal to m squared. So half m is equal to 3. Okay, so half m is equal to 3. So what do we have? We have that the quadruple PQMN, all the solutions, that's only one solution. So for I1, and then the quadruple. So if m is equal to p, so I implies that m has to be equal to p. So rather II implies that, so solving for II implies that m has to be equal to p. That is when we're solving for II. Okay, so have p, q, m, and n will be three, 5, 3, 3. Lots of 3s here. Okay, so that'll be it for this video. So I hope you enjoyed the video. See you guys in the next problem solving session. Goodbye.